So this activity, number 2, asks us to consider an inverted circular cone in which water is being added at a constant rate of 0.75 cubic feet per minute. So it's inverted. This is a good question for one of the groups. Why does it matter that the cone is inverted? Why do you think it matters here? Why does it make it easier if the cone is facing this way as opposed to turn this upside down and make a tank that's like shaped the other way?
Oh. It's easier to work with.
It's a lot easier to work with because when the tank is facing this way, what shape does the water always take? The water always takes, in fact, the same shape as the cone. Whereas if the tank were upside down, I just want to draw this really quickly. If the tank were like this, and I were filling it with water, then the water would collect in the bottom and it would have this weird shape like this, right? And this is a shape that if we care about the geometry in this problem, and we do a little bit in part D, this is a lot harder shape to compute the volume of than this, right? Because this is just a cone. This is a weird thing called a frustum, a circular frustum. So there are formulas for it. They're just not very nice. Anyway, so this question asks you to think about the relationship, and that is the whole theme of this first section, right, is relationships between changing quantities. The relationship between time and the amount of water that's in this tank. And in the beginning, that amount is specified by a volume. So what did you find when you did part C? How did you fill out this table of values that relates the time to the volume of water in the tank? How much water was there after 0 minutes? Let's start with that. None. The tank starts empty. How much water was there after 1 minute? How do we know that? Yeah, that's why this information is important, right? That when I know the rate of change of something, it gives me a way of converting in between an amount of time and an amount of something, in this case water, right? Volume of water, right? So that is almost like the conversion factor in between time, measured in minutes, and volume of water, measured in cubic feet, right? After 1 minute, there's 0.75 cubic feet. How many after 2 minutes? 1.5. Yeah. I'm going to just put little dittos here for these units. And so on and so on. What's this one here? 3.0. 3.75. Right? And so what did you notice about the graph? When you took these points, these values of t and v, and you placed them on this graph, what did you notice? What do you think was interesting about the graph that shows up?
It's linear.
It's linear. So that's a very specific observation. What does that mean? What does linear mean?
It doesn't change, it's just a constant rate.
Ooh, I like that. Right. So you're not only are you correct, you're sort of anticipating a lot of the kinds of discussions that we're going to have in this first chapter, right? So we plotted the points. You find out that the points lie along a straight line. Why do they lie along a straight line? Because the rate at which the volume is changing from one point to another is always constant. Why does it make sense that it's constant in this problem? How do we know that the rate at which the volume changes with respect to time remains the same? How could we have known that even without sketching this graph? Where is that information given to us? Yes, it's given to us right there, or if you like, right here in the original paragraph, right? So the fact that the volume is, by construction in this problem, changing at a constant rate with respect to time, that is why, in the graph, we find out that this is the volume has a linear relationship to time. When we get into section 1.4 this semester, linear models, linear functions, are kind of the most basic kinds of models that we can create, and they represent this constancy of change that you were talking about. So what happens then when we go to the other question, where instead of measuring, sort of trying to assess how the volume of water changes with respect to time, we instead think about height. So I want to hear from the Wednesday group real quick, because you had what I thought was a good way of thinking about how the height of water in this cone is going to change with respect to time, and maybe a different way than the volume changes with respect to time. So what was your argument? First of all, what shape was your graph?
It was at a...
Tell me about your reasoning. So you sketched a graph of height versus time that looks like this. So why is it curved?
Well, when the water first is in the cylinder, when it gets in there, it will it'll rise dramatically because there's not a lot of volume at the bottom of the cone.
Mm-hmm.
As the water rises, the volume opens up more, therefore there's more space for the water to, spread out, and therefore the height won't rise as dramatically.
The height doesn't rise as quickly. Right. Great. That's really well said. What I would encourage, if you're not quite tracking with what you just said yet, think about it this way. If I have just a little eyedropper of water that I want to put into this tank, and I put that eyedropper of water way down here at the bottom, how much is the height of the water going to change? Probably quite a bit. Whereas if I have a mostly full tank and I put an eyedropper in, how much is the height going to change?
Not much.
By only a little bit, right? Because that eyedropper full of water has to spread out over a larger area, as you were saying, at the top, than it would toward the bottom. And so that explains why it's not a straight line. But your explanation also explains why this curve curves in the way that you say, right? That it starts out at the beginning, a little amount of time produces a larger change in height, and later on, as the tank is getting more full, each little bit of time, each eyedropper that I put in, is only increasing the height a little bit less. Right? Were there any other different shapes of graphs that people came up with in their groups for this possibility of height versus time? So one of the things that this predicts, and when you do the reading for 1.3 between now and Wednesday, this is the main topic that you're going to be thinking about, is that how a quantity changes with respect to another, the rate of that change, really is what tells us what shape the graph is going to take. Right? That for my linear function, this linear function is a reflection of a rate of change which is constant. It's changing in exactly the same rate from one point in time to the next. Whereas in this example, I would say that the rate of change is a larger number over here, a faster rate of change in this part of the graph than it is over here in this sort of shallower part of the graph. So the rate of change itself can change. It can vary in different places. When it doesn't vary from place to place, we get a linear graph. But when it does, we can get curves. And that rate of change determines for us the shape that the graph ultimately takes. Last point I want to make about this is notice that what we're not doing right now is we're not using many formulas. We're not doing much algebra. We're not even really doing much geometry because we're not being asked to be specific about these relationships. We're just thinking about the relationships. But we're thinking about them in a variety of ways, right? And the way that I like to do it first is think about just data. Just think about getting some numbers. Get your table of observations, your ordered pairs. This is often in sort of the real world when we come up with opportunities to do algebra and pre-calculus and calculus. That's where our relationships tend to come from. They tend to come from data. And then once I have data, I can then convert that data into a visual, put those ordered pairs on a graph, and see what trend is being suggested. And pictures speak 1,000 words and so forth, right? And by the way, since we're in a math class, we can also eventually use formulas in algebra to talk about this, right? So those three different sort of uniquely mathematical ways of understanding a relationship, all three of those are going to be equally important for us this semester. I want us to understand every concept and how it is reflected in a table of data, and how it is reflected in the shape and other features of a graph, and how we can understand its connection to the algebra, right? So I want us to be able to speak all three of those languages. And then on top of it, of course, we layer the English language. So it's really kind of four different ways of speaking math. So when you hear me come back and refer to those algebraic, graphical, numerical, and verbal ways of communicating, that's what I mean, right? We're going to be speaking all four of those languages this semester.